Well, hello, and welcome to Doc Onco's Physics. My name is Keith Onco, and today what we're going to be doing is taking a look at combination, parallel, and series circuits. In previous lessons, we've taken a look at series circuits and parallel circuits, and once we've gotten good at those, what we need to do is take a look at what happens when we actually combine a series circuit and a parallel circuit. In order to analyze a combination circuit, what we need to do is we need to use aspects of the analysis of series circuits and aspects of the analysis of parallel circuits in doing the analysis of the combined circuit. So up on the top up here, what we have is we have a parallel series circuit. So this guy here is a combination circuit. How do I know it's a combination circuit? Well, first of all, I know that it's not just a series circuit because the definition of a series circuit is there's only one path for current to flow in. I know that it's not just a parallel circuit because I have resistors that are not in parallel, right? This resistor up here, resistor R3, is not in parallel with resistor R4, okay? Resistor R1 is not in parallel with resistor R2. Okay, so we have a combination circuit. How do we analyze this? Okay, well, what we really need to do in order to analyze a combination circuit is to take the circuit and simplify, 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 until what we have is a totally simplified circuit that looks like this one here. It looks like just a plain old series circuit. That's ultimately what we're looking for. But the key is in getting there. And in order to get there, we have to be able to recognize resistors that are truly in parallel and resistors that are truly in series. Because what we're going to do is we're going to take resistors truly in series, we're going to combine them as we can combine series resistors, and create an equivalent resistance for that. We're going to look at two resistors that are truly in parallel. We're going to combine them into an equivalent resistance, create a new circuit, all right, and then continue the simplification process until we finally have this guy right here, and we can get the basic circuit information. Once we have this circuit, we can find out what the total current is in the circuit, all right, I total. The total voltage of the circuit, which is, well, we know that to be 120 volts right here, the total resistance of the circuit, and then we can take the information that we have and work backwards and backfill in information. Okay, so that's how we analyze a combination circuit. So let's first look at how do we know if two resistors are truly in parallel? Well, two resistors are truly in parallel. If we look at the left-hand side over here, I've got some rules stated. Two resistors are truly in parallel if the top of the first resistor is directly connected to the top of a second resistor, and the bottom of the first resistor is directly connected to the bottom of the second resistor, and there is nothing else in between. No other resistors or components or anything else in between. The only thing that can be in between would be a wire. None of the resistors in this circuit are truly in parallel yet. Okay, we need to simplify it in order to get there. However, if I were to draw a circuit like this, say this is R1, this is R2, all right? These resistors are truly in parallel. Why? Because the tops of the resistors are connected with no other components in between. There's only a wire between them, and theoretically our wire is just like a single point. If we look at the bottoms of the resistors, they are also connected together with nothing else in between. So I can combine these resistors into a single resistance. right? I can find an equivalent resistance for R1 and R2 using the reciprocal formula to create an equivalent resistance, which I would call then R12. Right? Why do I call it R12? Because it's a combination of resistors 1 and 2. The other really important thing to do as we're simplifying circuits is to label things really, really well. Okay? So that's how we know if resistors are truly in parallel. How do we know if resistors are truly in series? Well, over here, again, oops, I'm sorry. Gotta go up. Resistors are truly in series up here, right there. If one resistor is connected to, or one side of one resistor is connected to one side of another resistor and nothing else. Okay, so let me repeat that. One side of one resistor is connected to one side of another resistor, and neither one of those resistors on those sides are connected to anything else. So let's look at our circuit over here and see if we can find an instance like that. Well, resistor R3 here is connected to resistor R4, right, on one side, right? So we have that met, right? The other sides are connected to, can be connected to anything, and that's fine, because we're really only concerned about this side. And these resistors on this side are not connected to anything else. So these resistors, R3 and R4, those are truly in series. Okay? Let's look at, say, R1 and R2. R1 is here, R2 is here, right? Are these truly in series? Well, if we look here, all right, one side of R1 is connected to one side of R2, so it meets that requirement. However, okay, both R1 on this side and R2 on this side are connected to another resistor. Okay, all right. The criteria is that R1 on this side must be connected to R2 on this side and no other components. The problem is they're also connected to R3. Okay, so these are not in series. R1 and R3 are also not in series for the same reason, right? They're connected, they have this connection right here, right? This side and this side, they're connected, but they are both also connected on that side to resistor R2. So they are not truly in series, okay? So the only thing we truly have that are in series are R3 and R4. Are there any resistors that are truly in parallel in this circuit? Not that I can see, right? Because these two look like they're in parallel, right? But while the bottoms are connected with nothing else in between, the tops are not connected with nothing else in between, and so they are not in parallel. So we want to simplify. How are we going to simplify this circuit? Well, I'm going to combine R3 and R4 into a new resistor called R3R4. Okay, what's the value of R3R4 going to be? Well, these are series circuits and series resistors. And so how do we add series resistors? We just add them up, right? So R3 is 5 ohms, R4 is 15 ohms, and so R34 equals 20 ohms. Okay, now we're going to bring down the values that we already had up here. So R2 is 60 ohms, so that remains 60 ohms. R1 is 25 ohms, that remains 25 ohms. And R5 is 20 ohms, and that remains 20 ohms. Okay, so we now have a new circuit. We have an intermediate circuit. We're getting there. Okay, we're still not in a position where we can get total resistance or total current yet, but we're getting there. Now we're going to look at this circuit again and say, okay, how can I simplify? Do I have any resistors that are truly in series? Not that I can see. Do I have any resistors that are truly in parallel? Yeah, I do. All right. These guys here are truly in parallel. Their bottoms are connected to each other with nothing else in between. Their tops are connected to each other with nothing else in between. I can combine R2 and R34 to create a new resistor, right, which I'm going to call down the bottom here R234. When I combine the 60 ohm resistor and the 20 ohm resistor, these are in parallel. I can't just add these up. I'm going to have to use the reciprocal formula. So R equivalent in this case is going to be 1 over 60 plus 1 over 20. Right? And when we do the math there, what we get is 15 ohms. So R equivalent of R2 and R34 becomes 15 ohms. And so R234, right down here, is a 15 ohm resistor. Well, now what I've got is I have a series circuit. It's the simplest kind of circuit that I can have. Right? So I can find out all kinds of good information. I can get I total, right? Because I know what R total is going to be. R total is just going to be the sum of the three resistors. So I have a 25 ohm resistor, I've got a 15 ohm resistor, and I've got a 20 ohm resistor. When I add those up, I get 25 plus 15 is 40, plus 20 is 60 ohms. That's the total resistance from my combination circuit. Can I get I total, which is the current leaving the battery now? Absolutely. I total is going to be V total, which is 120 volts, divided by R total, which is 60 ohms. I'm sorry, it should be 60 ohms there. Let me erase that. Put a number in there. This is going to be 60 ohms. And so what's my current? 120 divided by 60 is 2 amps. My total current leaving the battery is 2 amps. All right, so what can I find out now? Well, I can find out a couple things. If I wanted to know the voltage drop across R1, remember voltage drops across resistors, I can find that out because I now know the current that is going to flow through this entire series circuit, right? Flows through R1, flows through R234, and it flows through R5, right? So the voltage drop across R2 is going to be the current times the resistance, so it's going to be 2 amps times 25 ohms, all right? So what's my voltage drop? 2 times 25 is 50 volts. So V1 is going to be 50 volts. By the same token, I can find the voltage drop across R5, which is the 20 ohm resistor. I still have the same 2 amp current flowing through there. So V5 is going to be I5, which is I total, 2 amps, times 20 ohms, right? And that turns out to be 40 volts, right? So I've got 40 volts across R5. So what's my voltage across R234, and how can I use that? Well, again, we know that R234 is 15 ohms, so V234 is going to be equal to 2 amps times 15 ohms, right? And that's going to be a 30 volt drop, okay, across V234 equals 30 volts. When I add all these voltages together, I better come up with 120, and I do. 50 and 30 is 80, and 40 is 120. Because remember, the voltage rises and the voltage drops around the loop in a circuit have to add up to 0. All right, well, now what we want to do is we want to take this good information and bring it back up. So what's the voltage drop across R1? Well, we know that to be 50 volts. Voltage drop across R5 was, that was 40 volts, right? 40 volts. Well, here's the interesting thing that we can take now. The voltage drop across resistor 234 is 30 volts. That's from this point to this point. Let me do that in red so you clearly see that. From this point to this point, we have 30 volts. Well, that's resistor 234, the equivalent resistance. That's the same as these 2 points here, because remember, resistor 234 is the same as R2 and R34 in parallel. So what's the voltage across those two resistors? It's 30 volts from this point, right, to this point. I have 30 volts. Can I then figure out my current through R2 and my current through R34? Absolutely. I2 is going to be the voltage across R2, which is 30 volts, divided by the resistance of R2, which is 60 ohms. So I2 is going to equal 0.5 amps. Okay, I now know the current through R2. Can I get the current through R34? Absolutely, in the same exact way. All right, I'm going to do it over on the left-hand side of the screen here because I've got more room. I34 is going to be equal to the voltage, right, which is still going to be 30 volts, divided by the resistance, which is 20 ohms, right? And 30 divided by 20 is 1.5 amps. Okay, so I34 equals 1.5 amps. Now, notice that the 1.5 amps going through this part of the circuit here, added to the 0.5 amps going through that part of the circuit, what does that add up to? It adds up to 2 amps, which is the total current of our circuit. Because remember, the total current leaves the battery, goes through R1, gets to this junction point here, and it splits. Some of it goes through R2, and some of it goes through R34. And now we actually know how much, right? We have half an amp going through R2, and we have 1.5 amps going through R34. We can then finally take that good information and apply it up here. Okay, so we still have 2 amps leaving the battery going through R1, right? We've already figured out the current going through R2. That's half an amp. Okay, notice how I'm just taking the information from the intermediate circuit and I'm bringing that information up to our primary or original circuit. How much current is going to go went through R34? 1.5 amps. So that current that's going to go through these two resistors is 1.5 amps. Okay. Can I now find the voltage across R3, the individual voltage across R3 and the individual voltage across R4? Absolutely. All right. So the voltage, I'm going to change it to black here. The voltage across R3 is going to be the current times the resistance. So what's the current? It's 1.5 amps. What's the resistance? 5 ohms. What's the voltage? 1.5 times 5 is V3 equals 7.5 volts. Okay. What's the voltage going to be for V4? Well, we're going to do the same thing. V4 is going to be, again, 1.5 amps. Okay, because the same current is running through each one of these resistors. These are series resistors, R3 and R4 are. 1.5 amps times 15 ohms. All right? And when we do this math, V4 turns out to be, 22.5 volts. 22.5 and 7.5, if we add up the voltage across R3 and the voltage across R4, it better come to 30 volts because remember we had 30 volts across R34. All right, well, the sum of the voltage drop across R3 and R4 should come to 30 volts. Okay, so this is how we analyze combination series parallel circuits. We break the circuit down, we simplify, simplify, simplify until we have the most basic circuit down here. We get as much information as we can out of this. We can get I total, we can get the voltage across these resistances, we can get the total resistance, and then we start applying it backwards. All right, so we apply it backwards to the intermediate circuit, find out as much information as we can, and then finally apply it to our original circuit, and again, find all the information that the problem is looking for. So this is combination series parallel circuits. I will have other solved sample problems on combination circuits because there's quite a few different kinds you can have. I'll put them out on the website or on YouTube, and I hope this helps. Thanks for watching.